Okay, so the goal here is to look at the electric field due to a point charge. Okay, so let's just get started. Suppose that I have the origin here, and I have some charge Q right there. And I want to find the electric field at some other point right there. Okay, so let's call that R. So this is the vector R that I want to find. Actually, that's R. Let's call that R1. That's where I want to find the electric field at, that position. Okay, and then I also know the location of this charge. I'll call that RQ. So I know both those charges. If I know that, if I know those two, I can find this vector, the vector R, from the point charge to the location that I'm interested in. Okay, so since I have vectors here and they're all adding up, essentially, you could write this in different ways. I could say, since I start here and I add the next vector at the end of the first vector, I can write this: RQ plus R equals R1. I mean, that's just your normal vector addition, graphical vector addition problem right there. So from this I can solve for R. R equals R1 minus RQ. And this is always true. If I have two vectors, the difference between those vectors is from the first vector to the second vector. So this is the change in, this is just like the change in position. You end up at R1, you start at RQ. Okay, so but I have that vector R. Now how do I find the electric field? Well, here is the experimentally determined relationship for the electric field due to a point charge. Now it may look crazy, so I'll write it up here. It's a vector, the electric field's a vector. That's it. Yep, that's it. So that says that the electric field at this point is equal to, it's a vector, it's equal to 1 over 4 pi epsilon naught is a constant. This is the electric constant. It has a value of 9 times 10 to the 9th newtons per Newton meter squared per coulomb. Yeah, right. And Q is the value of that charge. R is this is the magnitude of that distance squared, that vector squared. And then R hat is a unit vector that points in the same direction as R. If you don't have that R hat, then you don't get an electric field vector here. Okay, so you need that. Okay, so how do you find R hat? How do you find R magnitude? Those are the two problems that you have. So let's say I have R as a vector, R, and I'm going to write the vector components. This is the way we do it. It looks similar to something in VPython that we do it numerically. We have an X component, a Y component, and a Z component. And those three components make up the whole vector. So first, how do I find the magnitude of R? The magnitude of R is just going to be the square root of Rx squared plus Ry squared plus Rz squared. So all these components are just scalar values. So you can add them up, you can square them, you can add them, you can take the square root, and you end up with the scalar answer. Now what about R hat? Once I find the magnitude of R, and in fact, actually up here, if I square this, then that's just going to be Rx squared plus Ry squared plus Rz squared. Okay. So how do I find the magnitude of R? R hat is defined as the vector R divided by the magnitude of R. So if I have this as R hat, I could write that as the magnitude of R. I could write this in component form as Rx over R, Ry over R, Rz over R. Okay, but it's just a value. I didn't go over the adding and subtracting of vectors over here. I assume that you know how to do that from your previous physics class. So that's the electric field due to a point charge. And what the whole idea is, this is a very generic form. Now if I want to find the electric field over there, I just change the value of R1, but I don't, the calculation's exactly the same. Okay, now there's one other thing. What if I have 2 point charges? And this is something that we'll look at. Let's say I have a positive charge right next to a negative charge right there of the same value, Q. This is what we call a dipole. Now, we can find the electric field at any particular point right here, R1. The electric field at point R1, I'll call it E. It's just going to be E plus E minus. So this is the electric field due to this negative charge plus electric field due to this positive charge. Okay, so now the electric field due to each one of those, we're going to do the exact same way we do here. Okay, if they have the total charge of this dipole is 0, but since the distances between the two different points are a little bit different, then the electric fields don't actually cancel at this point. You do get an electric field, and this is the what's so cool about an electric dipole. Now, there's also a method for getting an approximate solution for the electric field due to a dipole along the axis and perpendicular to the axis. But if you just find any particular point and calculate it, you can do it that way too. Okay. So that's really the very basics of the electric field due to a point charge and due to a dipole.